Okay, sorry about the interruption, but I again pressed the wrong button. I don't want to redo it from the beginning, so we'll just carry on from where I left. I need to get used to this thingy here that I'm using to draw these slides. But luckily, I wasn't too far in the details of what I wanted to say, which is that. So we have a vector, which call it v, and we remember Pythagorean theorem, which says that the square of the cathete and the hypotenuse are related by the following equation. So let's call L the length of the vector, and L squared, so the length square, it's the sum of these two numbers squared. Okay, so if you square, so this, first of all, this is as you can see, this is the right kind of triangle that we are dealing with, because there is a 90-degree angle between the coordinate x and y. So this is not using it improperly. So there are these two lines here. Okay, let's make them red. 1 and 2. And if you square the length of these two components, you get exactly the length of the green line. Okay, so this is what this equation says. And okay, a little bit of notation that I might be using later on, not sure, but let's just stick with it. If we say that the length of the modulus, so the modulus, then the length of the vector v, which has this funny symbol, is L. We know that the length of our vector, I want to use this notation just because it's the length of the vector. If I say L when I change a vector, I may get in trouble. So let's keep even a bit heavy notation, but it's not harm. This is the square root of x1 square plus y1 square. Okay, so, and this is important because it gives you one important feature. So suppose this was the distance, the vector that tells you the distance of an object with respect to your position. You're here looking at an object down there, which is the blue dot. Okay, so you know that the distance is given by this relation here in flat spaces. So that's fine. We know it's useful. We will see that, for example, in quantum mechanics, this will give you a link to the probability of an event happening. So math is the same, slightly changes in the numbers that we use, but basically the length of the vector is very important to keep in mind. And the other thing that we want to address is the direction. How do I address the direction? So let's pick this angle here, and let's call this alpha. And we know that this vector can be associated to an angle. Why? Because if we think that the x-axis is associated to the angle alpha equal to 0, because there is no angle between any vector in the x-axis and the x-axis itself is 0, we can associate this angle here, which maybe it's around 30 degrees, I don't know, close to 30 degrees, and this will give us the direction. Of course, it could be minus 30 degrees this way, and will give us another vector, which we know it's this. I overshoot it, but maybe it was more than 30 degrees, maybe it was more than, I don't know, I'm not good at drawing, but let's keep this way. So you see what I mean? I mean, with an angle and the length, you can, it's equivalent of giving the two numbers. So I mean, is equivalent to giving the two coordinates, but this is another way to address um, the the specific of a vector. So giving the coordinate in another way, which is, as I said, angle and length. So the vector can be represented as a pair of number x1 y1, or but also can be represented by an angle alpha and the length L. And how do we connect the vector alpha to the other characteristic of the vector that we know, for example, the component? Okay, so this is a I will do maybe another video for just trigonometry, but let me just use it at the moment because I need. So we know that uh, as I said, in a triangle with this shape, with the with the 90-degree angle placed there in that corner, we know that the the, the height h is given by, this is L and this is the base and this is the angle. Let's call it alpha again. Okay, we know that h is L times sinus alpha, and also we know that b is equal to L times cosinus alpha. Okay, now in our settings, h is replaced by x1, L is replaced by modulus of L, and then we put actually no, x1 is cosine, was correct, cosine alpha, and y1, which is the height of the triangle, is times sinus alpha. For the moment, let's not fixate on what is cosine and sine. I can give you just a sketch in the next slide, but what I want to say is that any component can be written in these two in this parameterization, and vice versa. So if you have an angle and a length, you can find a component. If you have a component, you can find the length and the angle. Okay, and this okay, and as you can see now, you can easily rotate the vector by changing alpha. You can elongate the vector by changing v. And this is a very intuitive way to, for example, if we want to draw this vector here, we know that we have to move alpha a little bit further, but we also have to stretch the length. The coordinate will change, of course, in a particular way, which is not easy to guess. And this is where the matrices are coming into play. But let's go step by step. I want to first introduce you another bit of information that is important for the vectors themselves. Okay, so this is, by the way, this is related to the also what's called change of coordinate system. So if you ever heard about the circular coordinate system, radial coordinate system, where angles and radius of the circumference are involved, there will be some cosinus and sinuses in the change of coordinate, and this can be generalized also in 3-dimension. I'm not going to draw in 3-dimension because I'm awful. I will maybe do it in when I'll speak about qubit in quantum mechanics. There is a nice 3D representation of a qubit that you need it to describe it, but let's stick with 2D at the moment. Okay, so but I was going off a tangent, what I want to say is the one thing. So we have the vector. We don't need the triangle anyway because we remember it from high school, Pythagorean theorem. I will link it to the in the end of the video. So we understood that there is this relation. Okay. We know that there are two representations possible: angle and length, or coordinate. This is the set of coordinates that I will keep using and remembering. So let's keep it there. I can give you an idea of what sinus and cosinus is maybe later in the slide before talking matrices. But let's see if I can introduce another concept which is very useful in vector spaces. So if you remember when I started talking about vector, I said that is a set of element Fn. For example, it can be infinite, but let's keep it infinite, and the real number. And this was enough, and there was a plus operation between them, and there was also the product between a vector and a number. Okay, and this is enough to let's say call it a vector space. But there is a natural way to introduce another kind of product in a vector space that happens between two vectors. And I want to give it a pictorial notation which is very used. Not sure if it's not the only one, but let's keep it in, and I will use it also for other purposes later on. So let's use this kind of weird brackets. Okay, they're pointy brackets. Okay, and these are two vectors, and I want to define this as it can be, if you think about it, it's just a different notation as vector times 2, right? But this times can be used in other, also is an x, so it can be confusing. Usually vector, the product of vector of number is a point between two numbers, but for historical reason, let's say, we give a bit of more of decoration to this kind of product between two vectors, okay? And we want that to be not a vector in the end, but we want it to be a number a in the set of real number, for example. There are maybe, you can think about many ways to do that, but I will give you the one that is called the scalar vector product. Sorry, I will give a link in the slides at the end for who is interested. The scalar product. Why scalar? Because it's a product between two vectors that give you a scalar. A scalar is another name for numbers. I don't know the history of that. I don't know the details, but you can say that a number is a scalar quantity. Okay, it's not a vector. In fact, a number, it's a scalar quantity. And how do we do this? This is very easy. So what's the definition? So you go component by component. You have x1 and y1, and then you have x2, y2, and you place them in this bracket, magical brackets. And what you do is you literally take the first component and you multiply it by the second component. So you have x1 times x2, and then you add a plus, and then you take the second component and then you multiply it by the other component. So y1 plus y2. Okay, this is the definition of the scalar product. Okay, and as you can see, it goes component by component. And this is a number because the product of two coordinates, which are numbers, is a number, and the sum of two numbers is a number. So here on the right hand side we have a number, but the number is linked to the vectors component in this fashion. So we gave a rule to associate a number to two vectors. And you might want to say, why this association and not others association? Maybe there are other ways, maybe there are other reasons, but one simple reason is that if you, I mean, definitely there are other reasons. There is a whole theory about this scalar product and why they are useful. They induce matrices, matrix in spaces, and also all sorts of other things. But for now, we just link to the connection that we highlight before, which is what happens if you take the same vector twice and you do the scalar product. Of course, if you take the same vector and if you do the scalar product and you apply the rule, you will have x1 times x1. And if I draw what I say, it's easier, plus y1 times y1. But this is x1 squared plus y1 squared. So what we see is that this scalar product defined in this way, it's an easy way, okay, to find the length squared of the vector, the modulus square. Okay. I hope this is not confusing, but I will use it later on. This maybe this will be very useful when we will talk about quantum mechanics, at least qubit and simple 2D systems, which I will in future slides. But this is just an extra feature of the space. So we said there is a set of elements, there is the real numbers, you add them, you multiply by number, and also you have this kind of strange product here. And with all of this, we're happy with working with vectors. Okay. Now we want to do a step further and introduce the concept of matrix. And to do that, I need to just pause a second and get back later on. Let me pause.